Okay, so this is the file we used for basic deep neural network. We're going to use this as our base and learn to build a basic convolutional neural network. So I just made a copy of the same notebook and name it as CNN basic. And let me clear the outputs so we can start fresh. Yeah, so we still need NumPy. We can set a seed for pseudo random generation, and we'll need Keras. MNIST is going to be our data set. So CNN is supposed to work very good with MNIST or very good with image data sets. Right, we'll use the sequential way of building our model, and we'll need a dense network, and along with the dense network we're going to import a few more things. So con2d, and so this is for building a convolutional neural network, and we're going to also import a flattened layer. Okay, so few more layers we will import. We will do that a little later. So let me import these. Just collapse this. Okay, so if you want to look at, you can look at the images. So we're not going to use matplotlib today, but if you want you can. So let me just delete it. This is to import our MNIST dataset, and then you can check the shape. We did this yesterday. Xtrain.shape is 60,000 images. Each image is of 28 by 28, and ytrain is 60,000 labels. So you can name this whatever you want. But it's a usual convention to name the input as X and output labels as Y. And since it's a train data set, give a tag train, and this is our input, this is our output, and since this is a test data set, we give a tag test. So we also looked at our input data set and output label and test data set shape, X test and Y test shape. Okay, right, so we also plotted and saw. So you can do that if you want, right? And okay, so here is where we have to make some changes. So we flattened it out, right? So the 2D image 28 by 28, we flattened it out into a single vector, right? So let's make some changes here. So your convolutional 2D network will expect a 3D three-dimensional input. So the three-dimensional input, if I have to note it down, so it's usually in this order, that is rows, columns, and channels. So channels are the number of images you want to pass in one go, right? So since MNIST is a grayscale image, so it doesn't have more than one channel. It just has one channel, that is grayscale channel. So if you are working with colored images, you might have RGB. CIFAR 10 has RGB. We'll use that in a while. And but MNIST has only one channel. So this is the default number of rows, number of columns, and channels. And on top of this, you will also specify the number of images. So it's like number of images and rows and columns and then channels. So this is what is important. This is the shape of your input: rows, columns, and channels. So Keras usually takes channels as last. That's the default. If you want to move channels to the beginning, then you'll have to specify explicitly, right? So let me just change the shape. Okay, so we know xtrain, so let me do this. So xtrain.shape is 60,000 comma 28 by 28. So we can use this shape as it is, xtrain.shape. Okay, so that is exactly what we want. So if we want to specify explicitly, xtrain.shape of 0, right? So this is nothing but 60,000, the first index of xtrain.shape, that is 60,000, right? And xtrain.shape of 1 is 28 and 2 is again 28, right? So we can pass it as it is. So let's split it up like this. Okay, so this is the number of images, and you can also pass xtrain.shape of 1 and 2. So, or you can just say 28 comma 28 and the number of channels, right? So channels, number of channel is 1 here. So this is what is important. This is the shape of your input, right? So I'll change the same thing for your xtest. Right, so yeah, we have changed the shape, and now if we check the shape, so yes, you have 60,000 images. Each image has this shape, 28 by 28 into one channel, right? Okay, so we also do this. We also divide the images, the pixel values by 255 just to normalize it. Okay, we also looked at it, right? The output transformation is the same, so we keep it as it is, right? And yeah, so here we differ. So let me just delete it. So yeah, so this is important. Input shape, we prepare our input to a shape that convolutional neural network can understand, and in this format, and so that is something new. And then the way we build our model is also a little bit new. Okay, so it's again, our model is sequential, and then let's start building our layers. So model dot add con 2d, right? And let me choose the number of output channels. Okay, so what I'm going to give now is the number of output channels. So let's say I choose 32. So my first hidden layer has 32 output channels. That is what it means, right? Okay, so and my filter size or kernel size, let me call it kernel. So kernel size is 3,3. So each kernel that I'm using will be of the shape 3,3. And let me use padding. So if I want to use padding, I use the keyword same. So when I say same, the size of the shape of the input image and the shape of the output image will be the same. So that means we are using padding. It's 0 padded on all the 4 sides. So you get 1 extra pixel on all the 4 sides. So when we do convolution, we get the same image size. So there is no drop in the size of the image after convolution, right? So we've done padding, and we have to give the input shape like we did for DNN. So input shape is xtrain.shape. So this is the input shape, right? So once we fixed the shape for xtrain, so xtrain has 60,000 images. So this is a 0th index, and this is the input shape, right? So input shape is from the first index to the last, right? So I can do this from the first index to the last, right? And I also give an activation function. Now I can choose ReLU. Yeah, ReLU works good, right? Okay, so this is my first hidden layer. Now let me show you how to calculate the number of trainable parameters from your input to your first hidden layer, right? Right. So we calculate like this: input channels, number of input channels, right, into filter kernel rows, number of kernel rows into kernel columns into output channels, right? So in our case, this works out to be number of input channel is 1, and okay, let me do it here. Number of input channel is 1, and kernel size is 3,3, and output channel, number of output channels is 32, right? Okay, so this gives you all the weights, and plus we have biases, that is the number of output channels. Okay, so this is nothing but the bias. Okay, so number of output channels in our case is 32. So these are the trainable parameters. Oops, right, that's okay. So 1 into 3 into 3 into 32 plus 32, so that should be 320. Okay, so let's see, when we do model load summary, we should be able to see this, right? So this is between our our input to first hidden layer. Trainable parameters, right? Okay, so let's let's just have one convolution layer, and then we will slowly add some more. Okay, right? So like we did in our deep neural network, we need an output dense layer. So before we go to an output dense layer, since your image is 2D, the output image from your first hidden layer is still 2D, we need to flatten it out. So we use a flatten layer. Sorry, model.add. Right, so we just say flatten, so it will just convert the 2D into a single vector, and then we can add our dense neural network. So the output is 10, number of outputs is 10, and again activation is softmax. Right. So number of trainable parameters because of your flattened layer is 0, because we just simply flatten it out and pass it on to your dense neural network, right? So, but what's the size of your flattened layer? So that we need to calculate, right? Okay, So you have your shape as, so you have 32 channels, right? And each 32 channel is giving out an image of 28 into 28, right? So that is 28 into 28 into 32. So this should be your this should be the size of the vector that is getting into your dense network, right? So this value multiplied by 10 plus 10 will be the number of trainable parameters for your output layer. So for the output layer, right? So from flatten to output as trainable parameters. Yes, okay, so let's do this as how much. So it's this much. So then this much into 10, because you have 10 neurons at the output plus 10 for bias, right? So that gives you this much into 10 plus 10, so that makes it this much, right? So these are the number of these many trainable parameters you should have at the between your flattened layer and the output layer. Okay, right, so let's look at model.summary. Let me clear all this. Oops. Okay. Oh, okay, I should execute this first. Right, so we got our numbers correct, right? So yeah, this is our first convolution layer, so it shows none. So in place of none, we have the number of images, and the shape of each image, shape of the output of the first convolution layer is 28 into 28. So this is the size of one image. Number of output channel is 32. So you have 32 output channels, right? So we saw how to calculate this number of parameters here. This is the number of input channels into filter size or kernel size into the number of output channels, right? Okay, so your flattened layer just takes this and just flattens it out. So that is 28 into 28 into 32. That gives you this much. We did this here. And so this is the input for your output dense layer. So this into 10 plus 10 gives you this many trainable parameters, right? Okay. And yeah, okay. So how many filters are there? So how many convolutional filters are there? Or sorry, kernels are there? So yeah, so that is between your first input layer and your first hidden layer, that is your first convolution layer. How many filters are there? So yeah, so that is okay. So in this case, it is just 32. So we get that by, let me add it here, number of kernels. So this we calculate like this. Input channels into output channels. So that is, in our case, 1 into 32 equal to 32 kernels. Okay. And each kernel is of size 3,3. Right? So hope you get that. So these two things are important to understand: the number of trainable parameters and the number of kernels. Right? Okay. So when we add more layers, we'll see how to calculate this again. Right? Okay. So this is a simple convolutional neural network, and once we build the model, we can train it the same way. So right now I'm not going to change any of this. I'll just run it as it is, and batch size epoch and shuffle equal to true. And so training has started. So it won't do a big job because we have a very small convolutional layer and just 32 kernels. So but yeah, so this is how you build a CNN, right? And so once you train it, you can do the prediction the same way. If you want to round off, you can do that, or you can just get the prediction straight away. Give a array as input, numpy array as input, yeah, and you can check if the output is correct by this. Yeah, you can save the model the same way like we did. So let me say CNN here, right? Okay, so we are approaching 50% accuracy now. So let's do some prediction and see if we're getting anything near accurate. 50% may not be enough. Okay, so let me stop the training and okay, yes, as expected we are not getting. So let me remove this round off and see how far we've gone. What is y test of 4? So this is 0, 1, 2, 3, 4. So the fourth index should be close to 1. So this is 0, 1, 2, 3, 4. So it's still pretty far from our accurate value. Yeah, so as it trains, it will approach, right? Okay, so let's improve this model a little bit by adding one more convolutional layer, right? So I'm just going to copy paste this. So right now, when you learn, you need not focus on the accuracy. No, this we will eventually learn to get it better, but focus on focus on how to build models and how many parameters, how to adjust shapes, etc. Right? Okay. So I'll just put another model, right? Layer, another convolution 2D layer. So let me increase the output channel size, and let me also change the filter size to 5,5. It's a usual convention to keep it odd, and yeah, so that helps. Yeah, and padding, let me remove padding now. So I give the option valid. So when I say valid, we perform convolution on the valid space of the image, and we don't have any invalid zeros padded around the image. So since I don't do padding, my size of the image will reduce by 1 pixel on each side. So 2 on the row size and 2 on the column size, right? Okay, so I don't have to give this because this is my the shape is being fed from the previous hidden layer, and so I just need to give this much, right? Okay, so let's do the same calculation for this hidden layer, right? So let me just copy paste this. So we're going to do the same calculation between first hidden layer and the second hidden layer, right? The number of trainable parameters. So remember this formula: input channels into kernel rows into kernel columns into output channels plus the number of output channels for biases. So my input channel for the second hidden layer is coming from the first hidden layer. So first hidden layer has 32. So I take 32 and my kernel size has changed now. So I have 5,5 and my output channel size also has changed. Number of output channel is 64 now, and number of biases is also 64 now. So let me see how much is this. So this comes out to be 51264, right? So this many trainable parameters between my first hidden layer and my second hidden layer. So this is my first hidden layer and this is my second hidden layer, right? Number of kernels, so this is input channels into output channels. So in this case now input channel is 32, 64 output channels, so that gives me 2048. So this many kernels, and each kernel is of size 5,5, right? Okay, what happens to my flatten? So the size of the image has now reduced because of padding, because I did not do padding, so my image size has reduced now. The output of second convolutional layer, the output image size would have reduced by 2 on each side. So I forgot to mention this. So for 3,3 on each side, if you don't do padding, on each side 1 pixel will go, and for 5,5 if we don't do padding, on each side we will miss 2 pixels. So let me just note this. Output image size as 28 into 28 in this case because we did padding, and output image size in this case is 24 by 24, since the kernel size is 5,5 and we did not do padding. If we did padding, we would have added, Keras would have added 2 zeros on each side, so we would have got the same size as output. So that would have been 28 into 28. Since we did not do padding, we miss 2 pixels on each side, so we get 24 by 24. Right, so let me calculate the number of and the input for your dense layer after we flatten. So that is 24 into 24 into the output channels, number of output channels. So that gives as much. So it should be this many this many input to your dense layer, right? Okay, so for your dense layer, the flattened to the dense layer, the number of trainable parameter is this into 10 plus 10, so that is into 10 plus 10. Okay, so let's see model summary. Okay, so this is your first hidden layer, this is your second hidden layer, and this is just a flattened version of this, and this is the dense layer. So yes, did we? Okay, so the first hidden layer has output as this because we did padding, and so the shape has not changed. Our input shape is 28 by 28, and the number of output channels of the first hidden layer is 32 that we gave here, and the second hidden layer accepts these many channels, so that is what we saw here, the number of channels, and the number of output channel is 64, right? So the image size gets reduced to 24 by 24 because we have used 5 cross 5 kernel and we did not do padding, right? So yes, where is the, yeah, we calculated the number of trainable parameters, so it's correct. And flattened layer is just flatten this 3D array into a vector, right? Yeah, and this fed into the dense layer whose output has 10 neurons. So this into 10 plus bias 10, right? Okay, so I think I just explain a little bit about shapes. If you do not know it, it might help, right? So when we say 60,000 into 28 into 28 into 32, so this is what we mean. So when we say 60,000, we have 1, 2, 3, 4, and so on up to 60,000 values. Okay, so in this place we have 60,000. So when we go to the next dimension, so it comes down like this. So in this, so we have 28 items. So we have another array, each of having, say, 28. Let me use a different one. 1, 2, 3, 4, up to 27. Okay, so let me use this. 60,000 minus 1, that is 59,999, right? Okay, so we come down to the second dimension, and then we go to the third dimension. Each of the 60,000 has the second dimension as 28. So each of the 60,000 has 28 dimensions within it. And when we go down to the next dimension, we have each of the 28 has another 28. So let's say use this 1, 2, 3, 4 up to 27, right? And we go to the fourth dimension, 32. So each of this has another 32 things. So let's use another 31, right? So this is how you understand dimensions. So the first dimension is 60,000. So okay, let's come from the last. So 32 things. So you have 32 things, and so each of the 28 dimensions have 32 things. So each of these guys have these 32 things. So the first guy has 32, and the second guy has 32, and the third one has 32, and all the 28 has 32 items. And when we come one further up, so each of the 28 has this set, right? So each of these hashes have this set. And when we come one further up, so each of the stars have this entire set. So each of the 60,000 has 28 items in it, and each of these 28 items has 28 items in it, and each of these 28 items has 32 items in it. So that is how we understand shapes, right? So hope you get this. Right, so we're not going to execute this. Maybe I'll change this to a markdown cell, right? Okay. Right, so as usual, we can compile and fit and train. So this should give us a slightly better accuracy because we have added one more convolution layer, right? Okay, so again, I'm not going to wait for this. So you can try and train this and test it. So you should be able to get a better accuracy. Right, so I've used heavy batch size, so it takes a little bit of time. Maybe let's just see one epoch. So you're already getting a decent accuracy. I mean, in the first epoch, right? The very first round of images that it sees. So yeah, 14% is pretty good for first round of images. Right, so let me stop this. Okay, two more layers we should know, that is max pooling and dropout. So let's add those two layers. Max pooling 2D and dropout. So max pooling is to reduce the size of your images and just to keep the maximum of a set of boxes, maximum value of maximum pixel value of a set of pixels. So that will help you just retain the high intensity values and drop out the low intensity values. And dropout is a regularization technique. Maybe we'll discuss about that in more detail later. Dropout is will simply delete a percentage of your weights when you train. So this will kind of keep your model from overfitting and will help you understand if your model is big enough or small, so those kind of things. Right, so let's add those two layers. So max pooling is, you can add it after any convolution layer. So let's choose to add it after the second convolution layer, right? Okay, so I'll add it here. So model dot add max pooling 2D. Okay, pool size is equal to, so I can choose any pool size. So out of these 4 pixels, I will choose to keep 1 pixel value, and that will be the maximum of these 4 pixel values. So that is what max pooling does, right? Okay, so this is this works only for the forward pass. It has nothing to do with the back propagation, right? Okay, so if I use 2,2, so the image size gets reduced by half, right? So my rows get divided by 2, and so that gives, so the image size right now is 24 by 24. So 24 by 24 is 12, and so same thing happens for columns also, right? Okay, so I'll also add a dropout layer. So I need to specify the percentage of weights I want to delete. So let me choose 50%. 50% of the weights I choose to delete randomly. Okay, so the model does not overfit. Now when I drop out, I usually see the train accuracy will be less than your validation accuracy. So here I see my train accuracy is 14% and my validation accuracy is 17%. Okay, so as I train, this could change and my train accuracy could improve and my validation accuracy could reduce in the normal case. So but when I add dropout, the usual case is my train accuracy will be less because I choose to delete weights randomly. I choose to delete about 50% of my weights, so my validation accuracy is usually higher. So that means I have more space in my model, and my model is able to train, able to generalize well. So if my dropout is so if my model is smaller, then both my train accuracy and my validation accuracy will be less. And so that means I need to make my model bigger and maybe or reduce dropout a little bit, right? Okay, so let's do this. Oops. Okay, so I need to add this, import this, and then yes, execute this and model summary. Okay, so this is the output of your max pooling layer. Your rows and columns get reduced by half, and so there is no trainable parameter in these guys. Max pooling it's just a arithmetic step of choosing the maximum of the 4 pixels, and dropout just deletes your weight. Dropout actually has nothing to do in your forward pass. Max pooling has nothing to do in your back propagation, right? Flatten we already saw. So flatten will change for us. So now it is 12 12, so it will be 12 into 12, and the number of channels will remain the same, so that gives us this much, right? Okay, so this into 10 plus 10 gives us the number of trainable parameters in the last dense layer, right? Okay, so this should train better, and we've added a max pooling layer, so just to focus on the important aspects of your image, and dropout layer will keep it from overfitting, right? So let's compile and fit it. So let's wait for at least the first epoch. Here, so you can choose to add more layers like this. No, so it's a good practice to maybe keep the input a little small, and then swell in between, and then try and converge as you go towards the output side. So you can choose to have another convolution layer with, say, try and focus on the important aspects, say keep it 16 or maybe 24. Okay, reduce the kernel size to 3,3. And as we go deeper, it may not be necessary to do padding. Yeah, but it depends on what you're working on, right? So yeah, these things will change as per this. So you can add more layers, more convolution layers like this, stack them up, add maybe max polling and dropout after each of them, and so you can just add them like this. Yeah, the calculations will change, but you can just put them after each of the convolution layers. Yeah, but our image size is going to drastically reduce, so we should keep that in mind. Yeah, so if you're working with high resolution images, it's a good idea to do max polling, and dropout really helps in generalizing. So it's not a good idea to go beyond 50%. 50% itself is like half of your weights, right? Okay, so yes, we don't see a big improvement in the training accuracy, but you see your validation accuracy is higher in both the cases, and it should continue to remain higher because we've used dropout. And so the training is slower because of dropout, but it should generalize pretty well, right? Okay, so that's about basics of CNN.